Hi friends, this is Satishkumar presenting the third lecture in the microwave waveguides. In the last two lectures, I have told you about what is a waveguide and what are the similarities and differences of the waveguides compared with the two conductor transmission lines and coaxial cables. And in the second lecture, I told you about electromagnetic spectrum and different types of the band designations, okay, that will be available from various industry standards. And also, I told you about the different types of waveguides, or we can say the classification of the waveguides. Okay, in this third lecture, I'm going to present about rectangular waveguides. I told you already out of the five waveguides, they are like rectangular waveguides, circular waveguides, rigid waveguides, double rigid waveguides, okay, and elliptical waveguides. Out of these five waveguides, we have the first one, which is rectangular waveguide, which is what we are going to study here. Okay, so first of all, let us try to define what is a rectangular waveguide. If you look at the definition, a rectangular waveguide is a hollow conducting device with four sides closed and two sides open. As I mentioned you already, the name itself is representing the rectangular waveguide. It means the shape of the waveguide is like a rectangle. But in this rectangular waveguide, all the four sides are closed and two sides will be open. Through that open sides, from one side or one end, we try to apply or transmit microwave, which is a very high frequency signal, and from the other end, we'll try to take or receive the microwave signal. Okay, if we look at the shape of that rectangular waveguide, it will be exactly like this. If you look at this, the open end which is showing exactly in front of us, and in that open end, one end or one side, we can call it as the broader side, which we call it as A, or we can say it is the breadth of the waveguide, and another side which whose length is B, which is the width of the waveguide. Okay, and this is x-axis and this is y-axis. We place the rectangular waveguide in xy plane, and the direction of propagation of the microwave or electromagnetic wave will be along z direction, which is perpendicular to both. And this is the shape of a rectangular waveguide. And if you look at practically, the shape of the rectangular waveguide will be like this. Okay, through this end, okay, the one which is showing, we'll try to apply a microwave, and at this other end, we'll try to receive that electromagnetic wave which is being transmitted. And through this particular copper rectangular waveguide, the microwave will be moving from this end to that end by making total internal reflections. Okay, so this is the original microwave waveguide which we'll be using in practical applications. And if you look at the circular waveguide, which will be like this. Okay, as I mentioned you already, the circular shape guide, the front view will exactly look like a circle, and remaining everything will look like a cylindrical structure. So from this end, we'll try to transmit the signal, and at the other end, we'll try to receive the signal. Okay, this is what is circular waveguides, and by using this circular waveguides and rectangular waveguides, we design antennas which we call them as horn antennas. And this circular waveguide is giving us a conical horn antenna which we'll be using in our parabolic reflectors. For receiving purpose, we use this particular antenna only, the one which we will get from this particular waveguide. This is circular waveguide, and if we look at another waveguide, okay, which I'm showing you here, is a double rigid waveguide, we have even single ridged. Okay, I told you about the shape of this double ridged waveguide will look like H, but we'll have different types of shapes like all the alphabets. We can try to prepare this double we can try to design this double rigid waveguides. Here the particular H shaped double rigid waveguide will be seeing here, and this is where the signal will be received by using a coaxial cable, right? So these are the several types of the rectangular and other types of waveguides. Now we'll be coming back to this rectangular waveguides. In this lecture, I'm going to give you the different types of modes of propagation in this rectangular waveguide. What do you mean by these types of modes of propagation? See, if we want to go from one place to another place, let's say from in Hyderabad, from one place to another place. If we try to move from one place to another place, either we take a bike from this place to that place, or we can take a car, or we can take bus, or we can take a metro, or we can take some other kind of mode of propagation, mode of travel. Okay, so we have several types of modes of travel for moving from one place to another place. Just in the same way, in waveguide, once the wave enters into one end of the waveguide, while reach the other end of the waveguide, okay, it can take any mode of propagation. One mode will not be similar to other. Okay, they are called different modes of propagation. What are the various modes of propagation which are available in this rectangular waveguides? Okay, so this is what we are going to see now. As I have shown you already, this is the breadth of the waveguide, and this is the width of the waveguide. A, B are the dimensions of the rectangular waveguide, which will be generally expressed in terms of centimeters. Now consider a waveguide situated in the rectangular coordinate system, because we are taking rectangular waveguide, so we can assume it as in a rectangular coordinate system. Now, with its breadth along x-axis, that is A along x-axis, and width B along y-axis, and the electromagnetic wave is assumed to be propagating along z direction. So in the complete analysis, we'll always try to assume that the electromagnetic wave or microwave will be propagating in z direction only. Okay, now we'll try to define what is a mode. If we look at the definition of the mode, the electromagnetic wave inside a waveguide can have infinite number of patterns, which we call them as modes. Okay, so the electromagnetic wave inside a waveguide can take or can have infinite number of patterns, or infinite number of ways it will go from one end to the other end, and those infinite number of patterns we call them as modes. But we don't study about all those infinite number of modes. We will study here only 3 to 4 different types of modes, okay, which we call them as, okay, initially we see only these two types of modes, which we call them as transverse electric mode of propagation, or simply we call it as TE mode. Transverse magnetic mode of propagation, we call it as TM mode. This transverse electric mode of propagation is also called H mode, and transverse magnetic mode of propagation is also called E mode. Okay, I'll give you that later. Okay, and also there are two other modes of propagation which we don't study much here, but we'll try to see, and that is transverse electromagnetic mode of propagation. This is called TEM mode, and there is another mode also which we'll not study here, that is called hybrid mode or EH mode or HE mode. Okay, so these are the four modes that we have to see here, but we'll see more about this transverse electric mode of propagation and transverse magnetic mode of propagation, one which we call it as TE mode and a TM mode. So while analyzing this, we'll try to first assume that the wave is propagating in Z direction only. Okay, so first let us try to define what is transverse electric mode of propagation. Transverse electric mode of propagation. So let us try to define this. Here, if you look at this, if the electric field or electric field vector is transverse to the direction of propagation, it is called transverse electric mode or TE mode or H mode or H wave. Thus, in TE mode, no electric line is in the direction of propagation, so we get Ez is equal to 0. The definition looks like very simple, but it is a bit difficult for us to understand. Without seeing the diagram, we don't understand this particular definition. Okay, I will give you once again what is TE mode is. If the electric field vector is transverse means uh, perpendicular. Okay, so the transverse means perpendicular to the direction of propagation. I said already the direction of propagation is in the direction of Z, sorry, is in the direction of Z, so your electric field will be perpendicular to that Z direction. But he is not telling anywhere about what is the direction of magnetic field vector. Okay, for understanding this, we'll try to go for a very simple diagram. Here, look at this look at this TE mode of propagation, which is on the left hand side of this picture. In this TE mode of propagation, assume that here look at the rightmost, we have the direction of propagation which is into the screen, okay, which is into the screen. So for that direction of propagation which is going into this rectangular waveguide from this front end to the back end, which is open, both are open ends. If you look at these electric field lines, which are blue lines, which are perpendicular to that direction of propagation. Okay, so if you look at, this is the direction of propagation which is showing on the rightmost. For that direction of propagation, only these blue lines are perpendicular, and the other lines which are tangential to this particular particular waveguide, which are not at all perpendicular to the direction of propagation. So that's the reason these blue lines, which are electric field lines, which are perpendicular to this direction of propagation, are direction of wave propagation. That's the reason this particular mode is called as transverse electric mode of propagation. Okay, that's what is this. If the electric field is transverse to the direction of propagation, it is called transverse electric mode or TE mode or H mode or H wave. But why this Ez will be 0? Why this Ez will be 0 in this? Because we have assumed that the direction of propagation is Z direction. If you go back to our uniform plane wave, as the uniform plane wave which is in free space is propagating in Z direction, Ez as well as Hz both will be 0 for that. But why here only Ez is 0? Why not Hz is 0? Why not Hz is equal to 0 here? The reason is, if you look at the uniform plane wave, in that the electric field as well as magnetic field both are perpendicular to the direction of propagation. Okay, that's the reason Ez as well as Hz both will be 0 for the uniform plane wave propagating in Z direction. But here in this, only electric field is perpendicular to the direction of propagation, which is inside a rectangular waveguide. Of course, that inside a rectangular waveguide, the medium is free space only, but H field is not perpendicular to the mode of direction of propagation. So that's the reason this Ez will become 0 for TE mode and Hz will not be 0. Hz not equal to 0. Not equal to 0. This is what is the condition for TE mode of propagation. Now, we'll go to transverse magnetic mode of propagation, or TM waves, or we also call that is E waves. Similar to the definition of TE mode of propagation, we have this definition. If you look at this, if the magnetic field is always transverse to the direction of propagation, it is called a transverse magnetic mode of propagation. In this mode, no magnetic field is in the direction of propagation, so Hz is equal to 0, but Ez is not equal to 0. I'll be showing you here. Okay, this is the right hand side is the TM mode of propagation. Now the blue lines have completely changed and they are almost tangential to the waveguide. But if you look at these magnetic fields, okay, now the shape of the magnetic field is changed. And if you look at this wave propagation, for that wave propagation, okay, the magnetic field lines will be exactly perpendicular to it, but the blue lines, which are electric field lines, which are not at all perpendicular to the direction of propagation, which will be almost in the direction of propagation. Okay, if you observe them, it will be very clear. Okay, so that's the reason here, as the transverse magnetic mode is defined as if the magnetic field is perpendicular or transverse to the direction of propagation, it is called as TM mode of propagation, or E waves or TM waves. Okay, for that Hz is 0 and Ez will not be 0. In TE mode, Ez is 0, Hz is not equal to 0. In TM mode, Hz is 0, Ez is not equal to 0. This is what you have to remember. Okay, once again, I am giving you the same thing. As the direction of propagation is in the z direction, for TE mode of propagation, Ez is 0, Hz is not equal to 0. This is very important condition which you have to remember, because the complete TE and TM mode of analysis will be using these conditions. And for TM mode of propagation, Hz is 0 and Ez is not equal to 0. Okay, so this is about the two modes of propagation. Now we'll be moving to the third mode, which we call it as TEM mode of propagation. So this is transverse electromagnetic mode of propagation. If you try to define this particular TEM mode of propagation, this is the one in which both electric and magnetic fields are perpendicular to the direction of propagation. As we know, I said very clearly, in the uniform plane waves, when electric and magnetic fields both are perpendicular to each other, we have got the condition that is Ez and Hz both will be 0. If you observe, in the coming analysis, we will be trying to convert all the other fields components. Okay, if you look at these Ez and Hz, once you leave these Ez and Hz, what will be the other components that we have, that we'll be having? Okay, and one is Ex, another is Ey, Hx, Hy. These are the four components or field components that we will be having, and we express all these four field components in terms of these Ez and Hz. So what will happen when Ez and Hz will be 0? When you express all these four components in terms of Ez and Hz, and as Ez and Hz itself will become 0, then all these components will also become 0. When all the six components will become 0, this particular mode will not exist. Okay, this for this particular how when a mode will exist and all we'll be seeing at the end. Okay, but this is, I'm just giving you why the impossibility of transverse electromagnetic mode. Okay, for that I am giving you the explanation here. Ez is 0, Hz is 0, and we will express Ex, Ey, Hx, Hy in terms of Ez and Hz. As Ez and Hz are 0, then all these remaining four components will also become 0. That's the reason this particular mode will not exist. And the next mode which we have is hybrid mode, or He mode, or EH mode. hybrid mode or EH mode or HE mode. This is a mode in which both electric and magnetic fields are not transferred to the direction of propagation. In this, Ez is not equal to 0, Hz is not equal to 0. So this is a rare case which will happen in the waveguide, rectangular waveguides, and but we don't study about these hybrid modes at all. Okay, we'll be studying only about this TE and TM mode of propagation. The analysis is very important as far as the waveguides are concerned. Okay, we'll try to see both the analysis in the coming classes. In the next class, I'll be directly starting the common analysis of these TE and TM modes first. Then I will be initially starting with TM, and we'll see the analysis of TE later. Thank you.